Okay, welcome back, everyone. At the end of the last lecture, we found ourselves hip deep in conversion calculations. The main conversions we're talking about is between grams of a substance and moles of a substance, or moles of a substance and number of particles of that substance. So we went through a number of sample calculations, how to carry out these things. They all involved dimensional analysis, and ultimately we're now using dimensional analysis in much more of a chemical bent or a chemistry-esque type of looking at things, whereas before when we were learning it, it's sort of a lot of the problems we came up with were not very chemistry related, but now we find that using this dimensional analysis, we're able to carry out these conversions. So what I'd like to do is review the last thing we looked at in the last lecture, and that was find if given a mass of a compound, coming back and being able to calculate the mass of a particular element within that compound. And we had said before that this is sort of ridiculous and who really cares about that sort of thing, but it's going to feed into something that will have some merit. So last time we looked at this is what we ended with. We had a certain amount of this carbone compound, C10H14O, and it's asking for what's just the mass of carbon in 55.4 grams of that compound. And we found that with 55.4 grams of carbone, 44.3 grams of that is attributable to just the mass of carbon within there. It's sort of useless information, but we're trying to make a point here. It should be noted that if we take the two masses and divide one into the other, really the mass of the carbone compound divided into the mass of the carbon, we come up with a specific number, a ratio, and that's 0.80. If we multiplied that by 100, it would come up to 80%. So we can say that in this sample, 80% of its mass is attributable to carbon, always. Now, the interesting thing here is that it does not have to be just 55.4 grams of carbone. We can have any amount, and it will still come up with this same percentage, if you will, if we were to say double the masses. If we doubled the mass of carbone, well, at 110.8 grams, we would get theoretically 88.6 grams of carbon attributable to that. And I know that because the dividing one mass into the other gives the same amount. So 0.80 multiplied by 100 equals 80%. So really we can do this with any. If I have any mass of carbone now, 80% of that, if I multiply that mass by 0.8, is going to come up with the mass of carbon in that sample, and indeed any sample we work with. So we don't have to carry out this huge calculation in each of the cases, since now we know what percentage of carbon mass is in carbone. So we can actually take this calculation and turn it into a percentage calculation. And that's what we're going to be looking at next. This is the mass percent of an element within a compound. That's exactly what we did before, but instead of carrying out dimensional analysis on every single problem, we can distill this down to an equation. And that equation is as follows. The atomic mass of the element in question within the compound times the number of atoms of that element in the compound divided by the molar mass of the compound itself times 100, always times 100, because we're dealing with a percent here. So let's look at perhaps an example here, how we might be able to use this without going through the whole all of the dimensional analysis, which can sort of hold us up a little bit, because that's a lot of calculation. So here we are. Calculate the mass percent of chlorine in Freon 12, which is a refrigerant, and notice they give us the chemical formula. That's going to be important because we need to be calculating the molar mass of that formula as well. So notice in this example problem it says mass percent. What is the mass percent? Thus, that is a sort of a key that tell that you're going to be using the mass percent equation that we see here. So let's put that together. First, we have to calculate, as I said before, the molar mass of the compound, which we're conveniently given the chemical formula for, because we have to put that down here. And once we do that, we come up with 203.8. And now all we're doing is literally putting these things together. So we're looking for the mass of chlorine. Its atomic mass is 35.45 grams per mole. In Freon 12, there are 4 atoms of chlorine, and we calculated our molar mass of the compound. Multiply by 100, and there it is. Much less work, as we can see, than carrying. We could carry this out using a dimensional analysis, but every problem like this is going to come up with 69.58% mass percent of chlorine in there, so we might as well use this equation for mass percent. So here's another example. What is the mass percent of nitrogen in NO2? This is ostensibly a simpler one than before. Well, we have to find the molar mass of NO2, 1 times the atomic mass of nitrogen, plus 2 times the atomic mass of oxygen, and that gives us our atomic mass. And then we literally just plug in numbers. Well, 14.01 grams per mole, that is the atomic mass of nitrogen. And there's 1 atom of nitrogen in that, divided by the molar mass of the compound times 100, and here is our mass percent of nitrogen in that compound, using a lot less effort than we did before when we initially moved into that carbone problem. So through these types of calculations, grams to moles to number of particles or whatever, we can actually find from practical data, meaning gram masses from the laboratory, data that is not eminently obvious, that we can calculate these things that are what I call immeasurables. One of these immeasurables is something that I term the empirical formula. Empirical formula of a compound is the smallest whole number ratio of each element's atoms to each other in a molecular formula. So we're going to see a difference here between empirical formula and an actual molecular formula, which we've looked at before. And we'll look at these sort of one at a time to look at our examples. So we have a table here, and if we look at the top piece of the table, we're going to be looking at benzene. Benzene is a hydrocarbon, or it's an organic molecule whose molecular formula is C6H6. And here's a picture over here. We see there's maybe six carbon atoms and 6 hydrogen atoms. They just draw a picture there. It's not that important what it looks like. But we have the molecular formula C6H6. Now, can we make an empirical formula out of that? And it turns out we can, because if we look at the subscripts here on C6H6, each of those are divisible by the same number, or 6, if you will. And if we did that, we're going to come up with the empirical formula of CH. Ultimately, what this means is there's the same number of carbon atoms as there is hydrogen atoms in this molecular formula. We don't know what that molecular formula is, but we do know that it's a 1-to-1 ratio given by that empirical formula. So moving down, something like acetylene, which we see the gas in acetylene torches and make that very hot blue flame, C2H2. There's the name, and here is a picture rendition of its molecule. Is there a different empirical formula we can come up for that? And indeed there is. We look at the subscripts on C2H2. They can both be divided by 2 to give, again, CH as its empirical formula. So we find that while molecular formulas can be different, it is possible to have the same empirical formula. Moving on down, let's look at this third one right here. Glucose. Glucose is a complex carbohydrate molecule, C6H12O6. So is there an empirical formula? Is there a way we can reduce this by looking at those subscripts? And we would say yes, indeed, because each of those subscripts is evenly divided by the number 6. And if we did that with each of them, and it is important that we do it with each of them, we come up with our CH2O would be the empirical formula of glucose. Lastly, carbon dioxide is CO2 as its molecular formula, and in this case, the empirical formula is the molecular formula, because we find when we look at the molecular formula, we are unable to reduce that further. So CO2 being the molecular formula as well as the empirical formula in this case. So let's look at some examples of how we can calculate the empirical formula of a compound given a particular problem. And many of them are set out in the same way. We say, I have a compound, in this case, this example of phosphorus and fluorine. That's the compound. And it is decomposed into its constituent elements of phosphorus and fluorine. And we have some gram masses of each of those particular elements. Given that information, we can come up with the empirical formula of that compound. Now, these empirical formula problems, I like to set up as a table. You don't have to do that, but I like to. So that puts all of my information into a grid, and it works well for me. So if we look at this table down below here, I've put in our elements, phosphorus and fluorine. I know what that is because it tells me phosphorus and fluorine, and I put in their gram masses, which is also given. And now we notice how we move along here. We have our element and our grams. I had told you before, sort of a go-to when not really knowing how to carry something out. When in doubt, convert to moles, because if you're given a gram mass, if I don't even know step one of how I'm going to approach this, maybe I'll convert to moles and maybe get some partial credit or something like that. So I'm going to convert grams in this case, which are given, to moles. We can do that, and we'll see how that's done. Moving to a mole ratio, which is a simplified ratio of one molar amount to the other. And then we have to look to what's called a rounded ratio before we can get to the empirical formula. All of these we're going to be going through in detail. So our first one, going from grams to moles, how are we going to do that? Well, if we divide a gram mass by its atomic mass of that particular element in both of these cases, which we can get right from the periodic table, we find that we can come up with very easily the moles of each of these, 0.052 moles of phosphorus and 0.157 moles of fluorine. Now, molar equivalencies we like in nice whole numbers, because when moles are in whole numbers, they relate directly to the number of atoms of each of these elements in an empirical formula. So these molar amounts right here are anything but nice whole numbers, but we can force this into compliance here, which means we're going to get a mole ratio. This mole ratio over here is essentially a nice round number comparison between the moles that we see over here. The way to do that is look to your number of moles and divide each of them by the smallest number. We find in this case that the smallest number is 0.052, so we're going to divide both of these by 0.052, and let's see what happens. If we do that, we come up with this mole ratio that is more sort of equalized towards nice whole numbers. We get exactly 1, which makes sense because any number divided by itself is 1. And the next one we have is 3.02. So let's think about this. This is the result of experimentation of data from a lab. So why is it, we can make the assumption that this 0.02 on fluorine's mole ratio is probably is so close to 3, is probably the result of human error. So if we have that, we can using best efforts, we can round down. 1 to 3.02 is essentially 1 to 3. That's how we're going to be looking at that. 0.02 is insignificant, so it's a 1 to 3. And notice when I did that, we filled in these subscript boxes here, phosphorus 1 and fluorine 3. Now, obviously, subscript 1 is not expressed in these in an empirical formula or a molecular formula, so we just say that the empirical formula is PF3. So let's think for a minute. What we did on the previous problem was we saw the mole ratio for fluorine was 3.02. And we said, that's so close to 3, it's attributable to human error, so we just rounded down to 3. Well, at what point is there a limit to that? Is it half an integer or a tenth of an integer, or where do we get out of human error and into something else? And so we have to specify to what point we can consider human error and thus round down or up to the nearest integer on these empirical formula problems. But then above this particular threshold, which we're going to stipulate, well, other things have to occur. We have to manipulate these numbers some more. And we'll look at an example of that. So here it is. For our purposes, a deviation of less than or equal to 0.1 from any integer can be attributable to human error in these empirical formula calculations. So if it's 0.1 or less, is human error, and thus we're going to round down or up. In the last problem, we had it was 0.02 from an integer. So clearly that was well within this, this threshold right here, so we rounded down. However, if we run into an issue where we are over 0.1 away from an integer, this requires additional manipulation of those numbers, and it's not the result of human error. What this additional manipulation is how what we're going to be looking at in the next example. So there are a couple things at play in this next example. Sometimes empirical formula problems will represent the what is usually gram masses of the constituent elements in an empirical formula problem, not as gram masses, but actually as mass percents, which we saw in the last section. So let's look at this in this example right here. A compound contains mass percents of the constituent elements as follows: carbon 20%, hydrogen 2.2%, chlorine 77.8%. Determine the empirical formula. Well, at first look, usually we like to set these up in a table showing the chemical symbol of the elements, and then we had the gram masses of the elements, so that then we can convert to moles and then mole ratio and so on. Well, we don't have gram masses in this. We have mass percents. So we need to be able to convert to gram masses before we can start this problem. Well, if you'll remember, mass percents are for any amount of the compound. Any gram mass of the compound will always have these mass percents that we see here, whether it's 1 gram, 100 grams, 1 billion grams, or whatever. So we can determine how much of our compound we want. And I'm going to make that determination as exactly 100 grams. If we assume 100 grams of compounds, the mass percents on the top automatically convert to gram masses. 100 grams, 20% of that is 20 grams of carbon. We can do that. So now we convert hydrogen to 2.2 grams instead of 2.2%. Chlorine, 77.8% of 100 grams is 77.8 grams. So what I'm saying is, if you ever encounter a an empirical formula problem using mass percents instead of gram masses, this is a little trick that you can do to immediately be able to convert to gram masses. And then we're able to move forward and set up this problem in the traditional manner that I like to within a table. So here we go. What was the information that we were already given? Well, we had, here is our three elements, carbon, hydrogen, and chlorine from before, and here are our gram masses. These are always what will be given in the problem. And as we know, now we're going to move across the table and take our gram masses and first convert to moles. And we do this by taking the atomic masses of each of these elements found right in the periodic table and divide them into the gram masses to give our molar amounts. And here are our respective molar amounts right here: 1.67 moles of carbon, 2.2 moles of hydrogen, 2.19 moles of chlorine. So these are certainly not whole numbers. And remember, there was a way of forcing these into compliance by dividing each of these molar amounts by the lowest number, and that is the top one, 1.67. So let's do that and see what we get. If we divide each of these by 1.67 and move towards a mole ratio, well, certainly this top one is exactly 1 that we see right here, but look at the other two below it. Well, we have 1.3 and 1.31. This is a problem. This is a problem because we're not within 0.1 to an integer. So this is going to require additional manipulation. And this is where I define what that additional manipulation is. When we find ourselves in a quandary such as this, we are going to multiply each of these that we see here by the same integer number until we can find one that complies within 0.1 of an integer. Obviously, I'm not going to multiply all of these by 1 because I come up with the same number. So let's try the next integer, 2. If I multiply all of these numbers by 2, I end up with this series right here. Certainly the one on top is good. It's exactly 2. But again, we run into the problems encountered on the second and third. 2.6, 2.62, that's a problem because we're not within 0.1 of an integer. So we have to keep going. We'll take that original mole ratio and now multiply by the next integer, times 3. And let's see where that puts us. 3, that's good, exactly 3. 3.9, oh, that is equal to, less than or equal to 0.1 of an integer. That's human error. 3.93 is even closer, well within that 0.1 threshold. So now each of these can be rounded up. We rounded up to 3, 4, and 4. And notice when I did that, that plunked our numbers right into those boxes that are going to act as our subscripts in our empirical formula. So our empirical formula comes out as C3H4Cl4. So our last concept in this unit of study, we had been able in the previous two examples to calculate an empirical formula from mass data. And that's good. That's good information that we can't measure directly, and we now have an avenue into that. Now, an empirical formula, as I said, is important information. It's good information. But better information would be the molecular formula. If we can get the molecular formula, we not only know the ratio of the elements to each other, but we know their exact numbers. So if we have a little bit more information, we're able to calculate the molecular formula of a compound. And to do that, we have a calculation here where the molecular formula equals the empirical formula. Each of those subscripts in the empirical formula are multiplied by an integer, where n, 1, 2, 3, 4, and so on. So that n is always a whole number integer, or very, very, very close to it. So all we need to know is a little bit more information. And let's look at an example where we would be given that a little bit information. Now, here is our calculation. How do we get n, that integer? Because that's the only one we really need to know. We divide the molar mass of the compound by the molar mass of the empirical formula. So we have to know the empirical formula, first of all, to calculate a molar mass of it, and we have to be given in the problem the molar mass of the actual compound. We weren't given that before, but if we have that, then we can go ahead and calculate the molecular formula, which, as I said before, ostensibly is much greater, is better information. So let's look at this example. Naphthalene is a compound containing carbon and hydrogen, so two elements within there. Its empirical formula is C5H4. So that's great. They give us the empirical formula, and its molar mass in this of the whole compound is 128.16 grams per mole. Find its molecular formula. So here now I know this is a molecular formula problem because it's asking for the molecular formula. So I'm going to use this equation here, and the big thing I have to calculate is this integer. So the molar mass of the compound, well, that's here. I have that. And the molar mass of the empirical formula, all I have to do is calculate 5 times the atomic mass of carbon plus 4 times the atomic mass of oxygen. So if we do that, that comes out to 64.09 grams per mole. That's the molar mass of the empirical formula. So now we're just going to divide those two into one another. 128.16 divided by 6409, shockingly, we come up with exactly the number 2, or very, very, very close to the number 2. So that is our n value. So now all I have to do is take the subscripts in the empirical formula, which I have, and multiply them by 2 in this case. And we do that. So there's the empirical formula. Multiply each of those subscripts by 2, and we come up with the molecular formula. End of conversation. Okay, so that was the end of Unit 7, that unit of study where we were looking at these different quantities and being able to convert in between them. Well, we really haven't done a whole lot of chemistry. Taking the grams of sulfur and converting it to moles of sulfur is still sulfur. We haven't converted that sulfur into anything else. So finally now, it took 8 units, but we're finally into actually applying what we've learned thus far into chemical reactions, actual chemical reactions. And we're going to start off slow with a few salient features and then get into the main thrust of the chapter. So if chemical reactions is what we're talking about, let's look at some important considerations that we're going to have to work with. The first one would be more of a macroscopic sort of thing. What do we see in the lab? What are our observations that we see in lab? You can never tell really much of the time a chemical reaction is going on. You can't see the molecules making and or breaking chemical bonds to go from reactants to products. You can't see that. However, there are a number of tells that can tell you whether a chemical reaction is taking place. I should mention that I would say most chemical reactions are invisible. If you're just watching the reaction vessel, you can't tell much of the time whether a chemical reaction is taking place. There's analytical methods we can use to follow the reaction, but through straight up sight of our chemical reaction vessel, a lot of the times that is impossible. Sometimes not. So what follows are 5 evidences a chemical reaction is taking place. So let's take a look. The first one, if we have a color change from a previously clear solution, or we go from one color to another, we can assume that it's a pretty good bet that a chemical reaction is taking place. If we have the formation of a solid precipitate, we did that in earlier lab. A formation of a solid in a previously clear solution, we can again be inspired or be told that a chemical reaction is indeed taking place. If the product of a reaction does not always have to be a solid or a liquid or something dissolved, it can be a gas sometimes, and that gas can indeed bubble out of a solution. So when we see this sort of thing happening, we can say that, well, there might be a chemical reaction taking place because gas is being evolved in the chemical reaction. One caveat I might put into that would be boiling. If something is boiling, that is a physical change, not a chemical change. And yes, while gas is leaving the reaction, it is only the gaseous solvent, if you will, that is leaving the reaction. It's not a gas that's produced in a chemical reaction. So sometimes if something is boiling, well, it's just boiling. A chemical reaction is not necessarily taking place. However, if the reaction is cool to the touch and we still see bubbles coming out, that is indeed, we can be fairly assured that this gas is the result of a chemical reaction taking place. The emission of light. Now this would be a very cool reaction. Unfortunately, very few reactions actually are carry out this emission of light. But if your reaction flashes at you, and that emission of light is not the result of the reaction exploding in your face, well, then it's possible that light emission might tell us that a chemical reaction is taking place. Lastly, a very common one is the emission or absorption of heat from the reaction. So if heat is emitted in a reaction, if we can, as the reaction is progressing, we can hold on to that reaction vessel and see that it's warming up, that's an exothermic reaction. It's an exotherm. Whereas if that reaction vessel perhaps were cooling down, or we could measure the temperature increase or decrease, we could say, well, if it's going down, that's the absorption of heat, and thus an endothermic reaction. So that's a very common indicator, but you have to sort of be feeling the reaction vessel or taking its temperature of the reaction to see what's going on, but that would also be evidence of a chemical reaction. Another salient feature that we see when expressing chemical reactions, in particular chemical equations of reaction, are sometimes, not always, but sometimes we see abbreviations following the reactants and or the products to express their physical state. I would say most of the time that I personally leave that off unless it's necessary, but it's just to show you that sometimes we do see that. It's like, well, what is that little abbreviation after there? Well, now we're expressing that. If you see after a reactant or product in a chemical equation of reaction, the lowercase g, that would mean its physical state is a gas. Similarly, a liquid would be a lowercase l. A solid would be a lowercase s as an abbreviation. So that would be the physical state of these. A very common one is if you see AQ. Essentially, AQ means a dissolved state. So, and AQ is aqueous, meaning that for some reason, for whatever reason in general chemistry, a lot of these reactions tend to be carried out in the dissolved state in water. He seems to be the solvent of import in here. So we can say AQ would be a water solution. So we can really look at it as in the dissolved state. Now we can see a few of these. So here we have this. In this one we see our abbreviations, AQ, AQ. So these three are in the dissolved state, but here we have a solid, S. So that would mean that this stuff is a solid, so it's going to precipitate out of solution, given by that sort of down arrow I just drew there. But this is just for an example of a chemical equation of reaction, which does in this case have these abbreviations indicating the states of the reactants and products. So the last salient feature about chemical reactions, this is just to sort of set the stage for moving forward, are essentially all chemical equations of reaction, or rather most of them, can be put into four categories, types of chemical reactions. Now this doesn't have anything to do with exactly what the reactants are or what the products are, that sort of thing, but just the way they're set out or put across, we can they tend to fall into four general categories. And those four categories are as follows. So either a synthesis reaction, also known as a combination reaction, those are interchangeable. A decomposition reaction, we're going to find that that is the reverse or the opposite of a synthesis reaction. A single displacement reaction and a double displacement reaction. By looking at these, we'll look at some examples of each. We're going to be able to tell or be able to look at a chemical equation of reaction and say, okay, that's a double displacement reaction, that's a decomposition reaction, and so on. So let's take a look at some examples of each of these, and we'll start with a synthesis, or if you like, a combination reaction example. A combination reaction, here is a very general way of putting it, where we have reactants and products as variables. A plus X goes to AX. Here we are clearly taking two separate reactants and combining them into one. Therefore, we get that combination reaction. Again, this is also known as a synthesis reaction. An example might be the following. You don't have to pay too close attention to these pictures here. It's just a fun way of bringing to life a chemical reaction. But really right here, 2Na plus Cl2 goes to 2NaCl. Here, clearly we have two separate reactants and they're combining into one product. This would be an example of a combination or a synthesis reaction. The next one, a decomposition reaction. Now look at this, the way this is set up. This is exactly the opposite of what we looked at before in our combination reaction. In fact, if I turned around the reactants and products from the previous slide, I would have a decomposition reaction general sort of way this is put across. So here we are starting with one particular reactant, and clearly in the end we have two different separate products. They have decomposed, or the reactants has decomposed into these constituent products right here. So it's a decomposition reaction. An example of this would be the electrolysis of water. If we run a current, electric current through a sample of water, and here's water right here on the reactant side, we can come out with our two constituent elements, hydrogen, diatomic hydrogen, and diatomic oxygen, which we see here. So again, looking at this particular reaction, we would say, okay, this is an example of a decomposition type reaction. Okay, the third of four is called a single displacement reaction. And they say, well, AX plus B goes to A plus BX. Look at what's happening in this generalized reaction. We have, when we're in the starting material, that X is bound to A. And in the product profile, that X is now bound to B. We have displaced that X from one to the other. It is a single displacement reaction. Let's look at an example to see if we can recognize that in an actual chemical equation of reaction. So again, you don't have to look at the picture here, but let's focus on the chemical equation of reaction. CuCl2 plus zinc goes to Cu plus ZnCl2. These chlorines have singly displaced from the copper in the reactant profile to the zinc in the product profile. So this would have the shape, if you will, of a single displacement reaction. Lastly, a double displacement reaction. Well, in this case, this very general example, AX plus BY. Let's look at that reactant profile right there. And look what happens to A and B in the product profile. X and Y, double, have displaced. So where X was on A, X ends up on B. And where Y was on B, Y ends up on A. Two things displace. So therefore, it is an example of a double displacement reaction. An example, NaCl plus AgNO3. So here we go. here is our reactant profile. Let's look at the product profile. Well, the chlorine and the nitrate swap. Nitrate goes to sodium, and chlorine goes to silver. Two things, double. Two things displace, a double displacement reaction.